Next presentation is from Per Leander, Transrail, one of those DAS suppliers. The green button for forward.
I will try that. So, welcome. I started my career with a Master of Science some years ago, and later on and that was in physics. Later on I have been working on railways for 40 years plus, giving me some experience of this sector. From, I used to say, from screws to politics. So many of the aspects, and always directed to the development of the system. As for our company, Transrail, I started it in 1995, finding that the Swedish State Railways were moving too slow in my mind. Well, it's not very much easier to do it outside, I would say, but there is progress anyhow. And we started on the driver advisory systems technology in around the millennium, with the first implementations in 2011. So from there we have a lot of experience in the practical experience. Well, sorry, I should have pushed that one perhaps before I start this. Anyhow, I propose two subjects for today to Paolo, and one was about the fundamentals of eco-efficiency driving, and the other concerned more how you can improve capacity on the line using the systems like this. Paolo chose the fundamentals, so that will be the topic of today, and that brings us also back to physics, because I will not talk about the driver advisory system as such, but the physics behind eco-efficient driving. And that concerns all type. If you take it in the GOA, you have GOA 1 to GOA 4 as automatic driving, and so it covers all of these aspects. Anyhow, I would say that even more interesting may be that you can improve capacity of the line and the punctuality. We have shown in studies in the Stockholm area that we could increase the capacity of the public transport, the suburban train system, from 16 trains per hour to 24 without doing anything else than installing this type of system on board. So just a few terms and definitions to start with. It's a little bit complicated because you have a range of aspects concerning what type of information you give to the drivers. You start with the pure driver information, which is actually more or less, it was on paper earlier. You got the timetable, you got information about the speed restrictions and other instructions for the drive. And today you have it on a tablet or in some other way. On most trains you have cruise control, that is that the driver can decide that he wants the train to drive automatic at a certain speed, which is instead, of course it's type of automatic driving. And then you have the driver advisory systems, starting with the standalone, which is not standalone anymore in the perspective that it was started, but it's always connected in some way for external information, of course. And you have the CDAS, connected DAS, that it is connected to the traffic management. And in the Sphera development, which we have heard about, it has gone in two ways, I would say. One is the so-called CDAS-C, and that is that actually the traffic management side give the information on which speed the train shall keep in order to be at a certain time, at a certain point. But not taking very much consideration of how the driver is actually achieving this task. The other is CDAS-O, which is the onboard calculated data, and that is that you send just the timing points and so on, and the system on board will calculate how to drive. We have also, in the migration period, we have seen that there is a really need for what we call signal-connected DAS. That is, that you pick up information from the track side about the signal aspects, and that can be introduced into the DAS system. And that goes back to the aspect we had heard from SNCF Grisot about the problems of knowing where the trains are. And actually, the interesting thing is, do you have a red signal in front of you? We are also talking about intelligent cruise control. That is, that you don't run the train with constant speed, but you can actually run the train with a variable speed and letting the system itself control the speed of the train. And this is what we are actually very close to doing, or can do, with the system we have developed. So instead of using driving the driver as the controller of the train, he can decide that he wants the train to follow the advice that we are providing. And then, of course, you have the automatic operation with the standards SS126 and so on, which is actually very close to IRS 940, so it's more or less the same. It's just the format of the data. So, eco-driving. It's of course a question of how shall the driver drive it in order to obey all the constraints on the line and not to arrive to a signal when it's on red, but when it has just gone to green, if that is the best. So it's a matter of topography, the train configuration, the train data, the maximum speeds, and so on. And cost efficiency, if we talk about that. It's not only a question about energy, it's also a question about, it could be other aspects which are more important for some reason. Not driving too fast in a curve, for example, or something like that. So we are talking about the driving style. The driving style is something that the drivers learn from school, but they have very big problems to use it in reality. You have DAS and you have ATO. I will limit my presentation to energy now, because that's what concerns us at this time. And if we talk about energy, perhaps we should not talk about the energy as such, but in specific, I think kinetic and potential energy is interesting when you come to the driver advisory or this type of technology, because these are energies that you put into the train or that the train achieves when going on the line. And you have an interaction between. So kinetic energy can be used to motor the train uphill, and you will increase where you increase the potential energy, and then you will, of course, you will have, when you go downhill, you will increase kinetic energy by use of the available potential energy. So that just, but the important, of course, is the losses. I mean, energy is something, but you are interested in where are the losses, because it is the losses that you want to reduce. And you have running resistance. Well, I don't need to read all these points, but also but that includes also auxiliaries, HVAC systems, and so on. But that is not what a driving advice can provide, or what an ATO can assist you. It can only help you to improve the running of the train. If you take, and you have the number of modes, of course, motoring codes and so on. Just an example. This is a train run. You see the blue curve, which is how the driver has been driving. And you have the topography in the bottom, the gray. You have the red, which are the speed restrictions. And I have actually introduced a light, how does it work? Well, a light blue curve, which is the energy consumption during the run, or the energy consumed during the run, which we calculate actually from the speed profile that the train has followed, and by the mathematical model you can easily generate the information about how much energy was used. And if you do that, you get to the result looking like this, showing how the energy has been split in various losses. The traction system losses, the running resistance losses, and of course, if you have used you can use regenerative energy to recover some of the gross energy consumed and get it back as a net energy. So this is what the driver achieves. But is that optimal? Of course not. What you could do is to go like this. And if you optimize the running, you will have a situation where you have mainly, I would say, reduced energy consumption by reducing the traction system losses. And part of the losses is the regeneration of energy, that you send energy back from the train. So the result is that you have reduced the net energy consumption, but you have also reduced the regenerated energy, which is quite interesting, because that type of system means that you can solve very many of the aspects of storing or how you take care of regenerated energy. You simply do it by coasting, so you don't need to brake as much as earlier. It comes out like this, so that the energy consumption will depend on how long time you have available for the run. I've plotted a curve, so up to the left you have the max running as fast as possible, and the drivers normally go close to that. They don't know what will happen further on. They try to drive as fast as possible, but which they should not, of course. So you can save quite a lot of energy by introducing slack, extra time in the timetable, so that you can perform better and use coasting in a larger degree. And if you do that, you get something, comparing the two solutions, you will see the green curve as regards energy, and you have long areas with a really flat energy consumption. That is, that the train is actually coasting in these parts. In this case, you can see that the train is getting energy, but in the end, you have a long section with constant energy, which means that the train has actually calculated kinetic energy so that it can coast all the way up to the station, even if it's an uphill run. And this ends up with also with less power in the supply network. You will have less exchange of energy over the catenary, which also reduces losses in the catenary system, in the substations, and so on. So you are making a good profit out of that. Finally, you can talk about the type of algorithms used. I have been talking about the dark green curve so far, which is the optimal. But you can reduce the type of information to just a plain constant speed, or a constant speed involving some type of coasting. And the result is that you get performance diagrams a little bit like this, where everything depends on the savings you will actually do is how the driver position themselves compared to what the system should be able to give them in form of the curves. And the difference is also where are the drivers normally driving, and where is the timetable, available time for the drive. This one solution, it's not, and actually I think I just jump. This is okay as long as you had a train with very much regenerated possibility to regenerate energy. In case of freight, you don't have that. You need to, if you want to run constant speed, you need to use the brakes quite frequently, and that's the blue curve. And so it's a very huge difference if you can manage to make the train coast and use the the topography to reduce energy consumption, which is the green curve. And that will also affect how much in the bottom lines, how you are affecting the brake wear of the train. You can see in the diagrams, the upper one is the constant speed, where you have the red dots, which is mechanical braking, and in the lower diagram you have the red curve, which is much less, where you have using the variable speed. So, and finally, the timetable is important. How do you spend the time? How do you spend the total time between two end stations in the various legs, and where do you gain most by implying extra time? And that you can see in this diagram that you are losing quite a lot in the first legs, where you have to run as fast as possible and you need to brake. So, well, that was all of my physics lesson. Thank you very much.